Alrighty, sounds like we are live from Doug. Welcome everyone. This meeting we have going on right now is a precursor to Mainnet 2022 that's going to be happening in New York City on September 21st through 23rd. Today I've got engineer TJ Connolly from Fireblocks with me, and we are going to be having a little conversation about multi-party computation, also known as MPC, and talking to TJ about who his ideal mainnet panel would be to talk over MPC. So TJ, welcome. I'll let you give a brief introduction to yourself before we hop in.
Thanks, Chase. Great to be here and really looking forward to the Mainnet event. Incredible lineup of speakers and, industry thought leaders and industry participants. So, very excited to meet a lot of you listeners here, at that conference. So definitely looking forward to that. My background, I'm primarily come from a cybersecurity background. I started off my career, very focused on application security, software security, penetration testing. So lots of experience breaking things. And kind of identifying vulnerabilities and how to exploit them. And in the later half of my career, I've now been more focused on, building things and helping customers and end users, in a consultative manner to build things more securely. And so ultimately, over the last couple of years, I've gotten really into blockchain and, cryptocurrency and, the world of decentralized finance. So really when I heard of Bitcoin, I heard of Ethereum through, kind of attending conferences like Black Hat and DEF CON and kind of being in that hacker world, but didn't pay too much attention to it. Always thought that, perhaps there was going to be some regulatory crackdown on it, that, there was no way the US government was going to allow this to happen. This was all back in the heyday of, Edward Snowden leaks coming out and, backdoors and all of the most commonly used, cryptographic libraries from the NSA. So I didn't pay too much attention at first. And then what really piqued my interest was DeFi Summer. So DeFi Summer, we started seeing all these real legitimate use cases for blockchain. And it really opened my eyes to the technology. And so I've become very passionate about it since then. I do, kind of adhere to the core crypto ethos of, they are open, they are permissionless systems, they're composable. And really that, ultimately they're a better way to do business for everyone, guaranteeing more economic freedom and, less censorship. So that's what that's kind of my background. Today at Fireblocks, I'm an engineer. I work with customers in a consultative manner to adopt crypto and blockchain in a secure manner. Obviously, we know that there's a lot of vulnerabilities out there, a lot of exploits, but there's also an incredible amount of opportunity here. So that's my job here, and happy to be here and have this conversation with you, Chase.
Awesome. Appreciate the context, TJ. I think I share a lot of the common ethos and background interests with you as well. It is pretty amazing how far kind of like the security and the technology and that stack has come throughout the life of blockchain. So really looking forward to talking about kind of that tech stack today. So as we dive into kind of the world of multi-party computation, we asked this question at the beginning of all of these fantasy crowdcast mainnet panels. Who would be like your ideal fantasy lineup to have at mainnet to discuss MPC and securing blockchains with?
Yeah, so there's a lot of possibilities here, but the ones that came to mind that I ultimately decided on was three effectively of the leading cryptographers who have performed research on MPC and its practical applications, as well as its academic advancements in the fields of research. So that's going to be Silvio Mccauley. He's one of the world's leading cryptographers on zero knowledge proofs, which is a very core component of multi-party computation. He's also the CTO, I believe, of Algorand, and kind of leads the development there. Ran Canetti, he is, one of the other, industry leaders in this field. He's from Boston University, professor there. And then Shafi Goldwasser, she's one of the leading and introductory she really brought a lot of this research to bear. And so the interesting conversations that I think I'd like to get into with these individuals is, cryptography is it can be a very, binary subject. It can be either, an off or on thing. But I think there's a lot more to it. There's a lot more nuance. So with cryptography, there's always going to be a single point of compromise, a single point of vulnerability. And that point of vulnerability is always going to be the cipher. So in cryptography, you have a cipher, and then you have the corresponding cipher text. So let's say you wanted to encrypt, a string, you wanted to encrypt a sentence. In order to encrypt it, you need some type of key or cipher to then denote how it was encrypted, and then also, more importantly, how to decrypt it. So this is the difference between, encryption versus hashing. Hashing is a one-way function. You can't do it the other way. With encryption, the point is that you encrypt something so that it remains confidential. The integrity remains there, and you can authenticate the message, authenticity. And you could do that both, bidirectionally. And so really this conversation, I think, would be a little bit philosophical, where, and this is really where multi-party computation comes in, is that how do you eliminate that single point of compromise? Because it's always going to be there. If you're using encryption, either symmetric or asymmetric encryption, there's always going to be that single point of vulnerability where a private key needs to be used and shared in some form or fashion. So that would really be, the main topic, I think. So the practical applications, that we see today, public key infrastructure, we've kind of figured out a good model there through those cryptographic primitives to be able to share secrets in a relatively secure way. But again, when you start looking at all of these different advancements, you always come back to this same realization that there's still going to be a private key, and that private key is always going to be a single point of compromise.
Awesome. Yeah, great context and explanation there. I actually just dipped my toes into the world of MPC last week and came across a lot of these names that you brought up on your panel. So would love to see you speak with them in person at Mainnet. So I know you have a set of slides that might aid some of the Q&A that we'll be going into now. So if you want to pull those up for the audience, we can dive into the first set of questions, and pretty much just wondering how you would define multi-party computation kind of in like layman's terms for the general audience, and maybe provide like a brief example of how it might work.
Yeah, absolutely. So the formal definition, and so I'll give the formal definition and I'll give the kind of my informal definition. So the formal definition is that with multi-party computation, it's a technology that allows multiple parties to jointly compute a function over a number of different inputs while keeping those inputs private. So effectively what it does is it allows us, a number of individuals to compute something without revealing the value of what we're providing for that computation. And so this is really extremely useful in scenarios where you're in adversarial environments where no one trusts each other, but you still need to work towards, some type of common goal to get something done. In most scenarios, you would use a trusted dealer. So let me go ahead and just share a quick screen here to show you that. So in most scenarios, what you would require to do is, rely on a trusted entity. So the trusted entity here, this would be somebody that, okay, we can take the inputs from, party 1, party 2, and party, N, and we can take those inputs, read them, and then provide the answer to, our function. So the issue here is obviously that there's reliance on a centralized trusted entity. And, as we all know with blockchain and crypto, the biggest vulnerability is always going to be centralization. This is the ultimate factor that can really break these networks and make them, not work as intended. And so in this model, what are you sacrificing? Number one, you're sacrificing, your privacy. So each one of these inputs from each of these parties, the trusted entity is going to, be able to see those in clear text at some point. They're also going to, have the ability to potentially expose them to others. So there's lots of issues here with this, and multi-party computation is really just a way to take that trusted entity and remove it from the equation. So now with MPC, you can have, this model over here on the right, where you can compute a function or effectively do something collaboratively with other parties and do it without the reliance on that centralized trusted entity. So that eliminates that single point of compromise of, that trusted entity potentially being malicious, potentially having ulterior motives, and allows us as, these participants to be able to do something individually. And so a couple of different practical, more informal definitions. Really this is used for scenarios where no one really trusts each other. So, some basic examples here. Well, let me start with the very first practical application of MPC. And that was called the Millionaires Problem. And so this is from the 1980s. Andrew, I believe is Andrew Yao, cryptographer from the 1980s, effectively came out with this algorithm that said, if you have a group of millionaires, let's just say there's 3 millionaires, and they want to find out which one of them is the richest, how do they compute that? How do they determine that without revealing the actual amount of their net worth? So in order to do this effectively, they've, through a number of algorithmic steps, they, provide an anonymized representation of their net worth. They send it to the MPC function, and then it's able to compute which one is, the wealthiest, and without exposing the actual net worth of any of the participants, basically just a ranking system. And so this is a very simplistic application of it, but you can start to think about some more complex ones. So, electronic voting, obviously there's lots of issues and concerns and vulnerabilities that could be present in those scenarios. And I think that's something we're pretty far off from in our society from being able to really adopt. Definitely applicable today in the crypto world with things like DAOs and governance. So, voting and anonymizing voting, I think that's something we're going to see a bit of in the future. Things like a poker game. Obviously, you rely on a trusted dealer there. Any other game scenarios, things like that. You can use multi-party computation to effectively eliminate that single point of compromise. And then also auctions. So this was actually one of the most recent practical applications is with an auction system, typically you're, creating bids for, some type of good or service. But how do you anonymize that, and how do you find out who is the actual winner, who has the highest bid, without exposing the identity of those promoting the bids? And so this is, a great application of it. And this was actually brought to bear with a number of Dutch beets farmers. So this is an interesting thing that listeners might want to look up. But the Dutch beet auctions, I believe it was around 2012. Where their, MPC was really used effectively in that environment. So that's what MPC is kind of historically. I don't know. I'm sure we're going to talk about more practical crypto related applications, but at a high level, that's how it works.
Awesome. Yeah, I'll save some of my ideas for kind of how this could be applied in the long term in crypto once we get a little further into the discussion. Maybe you want to take a couple minutes to talk about how Fireblocks in particular is setting the standard for MPC for the rest of the crypto industry. When I was doing my research for my report last week, came across your guys' open sourcing of I believe it was the MPC CMP algorithm. And from my understanding, that's pretty much proliferated across the entire industry now.
Yeah, so important, clarity there. MPC CMP, yes, we've released that. We've publicly released the implementation of it. This is, you go to different organizations and they actually have different implementations of MPC. There's several of them out there, whether or not it's GG18 or, our MPC CMP. So there is a lot of nuance there, but in general, MPC is really the best thing at the current point for private key security in crypto. So, just kind of zoom out, I'm sure a lot of the audience understands this, but it's, always important to cover first principles. How does a blockchain work, right? What are the underlying cryptographic primitives that make it work? So the blockchain is a distributed ledger that's running somewhere, on a network through a bunch of different computers interconnected. And you as a user of that blockchain effectively have an account there. So you have a public key that says, hey, I'm a user on this blockchain network. And I have an account, and this account can have a number of assets or, entries within this distributed ledger. So this could be, hey, I own, 1 Bitcoin, or I own whatever it might be. And so that exists on the blockchain. But how do you prove to the blockchain that you're the actual one that owns that account and therefore has ownership of those assets and can transact from that account? And so that's where the public key where the private key comes in. So through the combination of a public key and a private key, you can create a digital signature. In addition to the public and private key, you're also going to need, some information about the actual message itself, such that the message can't be spoofed. But in general, you're always going to need the public, the private key, and then some type of input that denotes this is the message to be expected and to be signed. And so in crypto, in blockchain, the blockchain enforces, and it says, hey, if Chase comes to me and says, I want to move funds from, this account to another account, the blockchain says, okay, Chase, you can only do that if you provide the valid digital signature that proves that you own the account that you're trying to move the funds from. And so this is, ultimately really where all the security of blockchain boils down to is, that public-private key pair. And so this has obviously been where attackers have focused their efforts, whether or not it's, actual theft of the private key itself, which is, we know the old adage, not your keys, not your crypto. So, this is the holy grail of what an attacker would want to steal. But the other areas that they might steal or intervene in is the actual generation of like the transaction or the message. So if I don't have your private key, but I can manipulate your message before it gets signed and submitted to the blockchain, then I can do nefarious things like, switch the address from Chase's address to my address so that now the funds go to mine. And, Chase's wallet happily signs the message because it doesn't know otherwise. So MPC, this is an important note here is, it's not a silver bullet by itself. It's really a component of defense in depth and multi-layered security. So, we could definitely talk about some of those things if you'd like, but, I think it's important to highlight, especially, as, we're talking about this potential panel. I think that would be a big topic, right? This isn't a silver bullet. There's reliance on hardware, mitigation, software level mitigations, up and down the stack.
Yeah. I think it would be interesting to talk a little bit more about how, while it might not be a silver bullet, it does provide a lot of improvements over kind of like the standard ways to secure these things in a distributed fashion. So specifically on the private key side, we had the creation of multi-sigs pretty early on. So how do you see like this concept of multi-party computation being applied to shared private key management as being, an upgrade to the the multi-sig way of doing things?
Yeah. So multi-sig is a great technology. I'm not here to knock it. It is a great layer of defense in depth. In fact, there are ways to augment multi-sig with MPC. Vice versa, there are ways to use MPC in lieu of multi-sig and still take advantage of the same level and even more advanced levels of security controls that you can apply. And so, let's talk about that. So with multi-sig, effectively, all a multi-sig is doing is it's taking, a quorum of approvals and saying that, in order to sign a message, in order to produce that digital signature that denotes ownership of these assets in this account on the blockchain, instead of relying on just one private key, you effectively rely on several private keys to approve and sign that message. And so the issue here is that, you're still going to have that single point of compromise. Each one of those, approvers within that multi-sig, let's say it's, a three-person multi-sig, there's going to be three private keys there that are still going to be single points of compromise. So if I'm an attacker and I compromise, those three computers where those three private keys are stored or they're used to sign something, then multi-sig is effectively useless. And this is what happened in the Ronin hack. So in the Ronin hack, I believe they had about 4 or 5 validators. 4 of them were compromised, and then the 5th one was, basically like a default yes. And the attackers were able to compromise the physical systems of the 4 validators. And at that point, multi-sig, completely useless, right? The attacker has the keys. They have the keys to the kingdom. They can go ahead and, steal $650 something million. And so, multi-sig was an improvement, but it's not as well. It's not going to be a silver bullet. And so some of the other, kind of issues with it, obviously each one of those approvals is an on-chain approval. So it needs to be very specific to the protocol in which it's doing. So, multi-sig in Bitcoin is different than multi-sig in Ethereum. And, there's nuances between different chains and different protocols. It's also expensive from an operational, use point of view. So each one of those approvals in a multi-sig is going to be an on-chain transaction. So therefore, there's going to be gas fees incurred, that can get expensive very quickly. And then it's also, it's not very easily modified or composable. So with a multi-sig, if you want to regenerate or, redistribute who's the approvers, you effectively have to recreate the entire multi-sig and recreate the account as well. And so this is very, very challenging. So what we like to do, and, this is what we do here at Fireblocks, is, take that functionality that multi-sig provides, really the approve, either, sign or don't sign, and augment it and perform it off chain. And so what we do is we take the MPC component, which is producing the actual signature, and we separate that from the approval, which is happening with multi-sig. Multi-sig combines both the approval and the signing into one process. We effectively break them up. And so what that allows is that the approval process can now be much more granular and much more flexible. So instead of just saying in a multi-sig where you can just say, yes, I sign this, or no, I don't sign this, when you break those two pieces up, you can do things more complex, like, what if this transaction is over $100,000? What do I do? Does it go to Chase for approval, or does it go to TJ for approval, or does it go to, this quorum of 5 individuals? And so that's really, one of the main shortfalls of multi-sig. And, the ability to create that custom rules and logic and governance, according to your risk profile, is a much stronger way, we think, of being able to secure operational use of your private keys.
Yeah, I think the one thing that stood out to me was the fact that these like MPC enabled wallets pretty much look the same exact, and from an outside perspective on the blockchain, they look the same as just a standard single private key wallet. So all of these MPC nodes are kind of collectively signing one private key rather than bringing together a bunch of various private keys to sign the single address. And, that just creates so many different ways that you can extend the design space and kind of combine this with different blockchain applications. So, would love to dive a little bit more into what we touched on very briefly at the beginning about, like, what are some ways beyond just private key management that MPC could be extended to on the blockchain, and where do you think we're going in the future with those applications?
Yeah, so I think it's also important to talk about like what are the current bottlenecks that we have here as well. So obviously talking about the future, it's very easy to pontificate and say, okay, these are some applications of MPC. It's a lot harder to actually engineer and implement them, right? So thinking about technology and is easy. Building technology is obviously very hard. So really the bottleneck, up to this point has been the ability to perform MPC on secure hardware environments. And so, what does that mean? So in a computer, you have your main chipset, your CPU, that effectively is running, all of the code and applications and memory, for your computer. So if you want to do something, let's say secure, something like, compute a digital signature, and you do that on that CPU, all of the other applications that are running on that CPU are able to see that. You may believe the vendor that, hey, they have XYZ form of, protections and things like that. But ultimately, if I'm a bad guy and I have malware on that computer, or I'm a system administrator with root level access, I can always read your memory and steal that private key through some form or fashion. And if I can't steal the private key, at the very least, I'll be able to manipulate the message that is going to be signed and therefore, compromise its integrity. And so the bottleneck really has been, secure hardware environments. And so, historically, banks and the like have used hardware security modules. So these are effectively, dedicated chipsets, usually adjacent to a server, where, they'll store a cryptographic key. They'll perform very light cryptographic functions in it. But again, that's the issue. The issue is that the computational capabilities within HSM are very, very limited. And so what we've chosen to do is use Intel SGX. And so Intel SGX is a dedicated Intel chipset used specifically for secure hardware enclaves. And so what that allows you to do is now completely offload all of the core cryptographic functions that you would normally do on, let's say, the regular CPU or hardware security module. Now you can segregate that entirely on a secure hardware environment. And the only way to communicate back and forth through that secure hardware environment is coded specifically into the protocol. So if I'm a bad guy and I have compromised the server that is adjacent to the Intel SGX enclave, I'm not going to be able to reach into that Intel SGX enclave and read memory or see any of the messages in there. Only the authenticated code that's available to go in there, defined by very specific functions within that code, is able to go in. And so this has been the bottleneck historically, is that MPC is very reliant on what are called zero knowledge proofs. And these are very computationally intensive. And so the benefit hasn't really been there to do this on non-Intel SGX hardware enclaves because the computing capabilities haven't been there. But, Moore's law, we see that, year over year, computing power, is increasing exponentially. And this has made its way to, the secure hardware and confidential computing world as well. And so that's been the bottleneck. So, in terms of the future, we're definitely making progress here. So today, obviously it's private key security, taking that private key and breaking it up into, not a single point of compromise, multiple different shares, and distributing it across multiple environments to make it more secure and less vulnerable to attackers. The kind of future state here, in terms of like practical applications to crypto, one of the things that is most interesting to me is cross-chain messaging or bridging. Obviously, tons and tons of vulnerabilities there that we've seen. The largest, attacks, tracked by sites like Rect and these other and Masari as well, have shown this. to be the case. So there are practical applications there, right? For these cross-chain bridges, they're always going to rely ultimately on some type of verification of ownership of an asset on one or the other chains. And that is where, the public-private key pairs come in, and, MPC can come in as well. The other one is going to be DAOs. So, decentralized autonomous organizations, where you have, groups, whether or not they're administrators within the DAOs or voters and participants, where they can participate in these agreements, these voting, these governance issues, and be able to do it both securely as well as in a privacy preserving way.
Yeah, I think one of my favorite kind of things to think about in terms of the future applications is, this could be the underpinning cornerstone of kind of how we run an entire society or replace a government on these distributed platforms. So if you think about things like a census or just any economic health indicators, you need to understand the private and sensitive information from your general public, but there's a conflict of interest. You want to get that information out and known, so you can make decisions on it, but the individuals don't necessarily want to reveal that. But this provides kind of that silver bullet of how you can get to that point and make those decisions on a distributed group of information without revealing the privacy there.
Yeah. And so I don't have a crystal ball to be able to say what's going to be the next big application. I think it's really going to be driven by what, do we as consumers and end users kind of demand privacy and security for. So, obviously that example, I'd love to see more, better practices from, governmental agencies and things like that for implementing that. But there needs to be an incentive, right? So, we as users need to, vote with our feet effectively, and use products, use protocols, use government's a whole nother beast, but, vote with our feet effectively, right? It's never going to be a single, silver bullet, but we need to focus on the implementations and the solutions where it can have the best effect for us. So
definitely, yeah, it's one of those things that's going to take many years, decades to really play out, and we're just so early in kind of the whole journey of that. Pretty much like you said, threshold signatures and private key management are really the only widely adopted implementation of this technology so far. We do have some of the cross-chain messaging protocols like Synapse, Multi-Chain, Axelar, using a blend of MPC to kind of sign these cross-chain messages. And it'll be interesting to see if those can stand the test of time versus kind of the established glorified multi-sig consensus that we've used for cross-chain messaging. That's just not really working so far.
Yeah, and we don't want people thinking that, okay, we put MPC on our architecture and, all of a sudden this is a bulletproof, technology. Like I said, I've spent most of my career breaking things. Given it enough time, given it enough effort, given it enough resources, everything from a technology perspective is going to be breakable. It's just inherent to the fact that, hey, this is a system that allows you to do something of value. So there's always going to be the opportunity for a bad guy to take advantage of that. So, MPC, again, never going to be the silver bullet. There's, you can get very deep into the different implementations of it, the different, algorithms specifically of it. And you need to really understand, more importantly, kind of zoom out and understand what are the threat vectors for what I'm trying to do. So, cross-chain bridges, obviously very unique threat vectors there. You need to understand who is the bad guy, why might they be targeting me, and what are the possible threat vectors and attack scenarios that they might try that I need to mitigate.
I think that's a great way to wrap up, highlighting that, this isn't going to be the perfect solution. There will always be vulnerabilities, but, that's part of the process. It's just continuing to identify them, iterate on what's next. Maybe there will be something that completely replaces MPC in the future, but I'm excited to see kind of what spins out of it. So we're running up on time here. It doesn't look like we have any questions in the chat, but once again, TJ, thank you for taking the time coming on. As a reminder to the audience, TJ will be hosting panel at Mainnet in New York City, September 21st through the 23rd. You can follow the link that we'll throw in the chat here for $300 off tickets to Mainnet to come and see TJ speak. TJ, it's been a pleasure. And if you have any other parting words, I'll let you share them here.
Yeah, thanks, Chase. It's been a pleasure as well. Looking forward to the conference and meeting all the attendees. So thanks again.